Thanks for introduction and also thanks for the invitation. So today I'm going to talk about the surgery formula in Instanton theory, and everything to join with and some of the results I'm going to talk about is also joined with Boston theory. So right. So what is Instanton Floer homology? So this is a homology theory for three manifold and nuts. So for a three manifold, let's just say Y is a closed oriented three manifold. What we can do is we can associate a finite dimensional complex vector space, and it's denoted by a shepherd Y. This is the frame Instanton Floer homology. And also, if we have a nut inside this Y, then of course we'll in general also deal with links. Then what we have is the Instanton nut homology of this paired Instanton. And well, both of them are finite dimensional vector spaces. Of course, well, this is a homology theory, so you can expect there's a chain complex and associated with this object, and then we deal with how we have the differentials and then take the homology to get this thing. So there are some remarkable applications of Instanton Floer homology. They just list two of them. So for example, this helps us to approve of the famous long-standing property P conjecture. And also there is the proof that the polynomial homology detects the N of. Right, to make use some properties of the Instanton Floer homology either related to the topology of nuts or related to the representations of fundamental groups of the three manifold for us to establish these remarkable results. So this Instanton theory has been very useful, and so that's why I'm interested in developing some new properties about it. And so let me give a very brief idea about, a very rough idea about how this Instanton Floer homology is constructed. So just a very rough idea, and let me focus on the case where if we have a closed oriented three manifold and the construction for nuts and links are similar. So let's just say if we have this Y here, which is a closed oriented three manifold, what we do is we look at the SU2 bundle over this Y, SU2 principal bundle over this Y, and some obstruction theory tells us it's always trivial. And what we can do is we can take the space of our connections, our SU2 connections on this three manifold, and there is a Chen-Simons functional, which goes from the space of connections to the set of real numbers, and intuitively, the Instanton Floer homology is just the Morse homology associated with the Chen-Simons functional. So let me just write that intuitively. Instanton. Chern-Simons functional from yeah. So this is a workshop for the circle value of Morse function, and actually there are some symmetries on the space of connections that act by the gauge group, so the gauge transformations on the bundle. And so if we quotient out that gauge transformation, actually get indeed the quotient of this connection with gauge transformations to S1. And so I'm not going to say too much about the detailed constructions because there's a lot of like analytical work that we need to make sure that we have a finite critical point after quotient out with the gauge group, and also we need to deal with the negative flow line equation and to prove a lot of analytical results on that. But finally, we can package everything to become a well-defined, and this is a finite dimensional, and we use complex coefficients. Let me say complex coefficients. Okay, great. All right, so yes.
Is A a manifold?
Well, it's not a manifold. I think this is an infinite dimensional, and it's an affine space over some bundles over our base manifold Y. And so, yeah, this is an infinite dimensional setup for Morse theory. So, but there are two key takeaways I would like to stress here. Right, so one thing is that, well, if we look at, well, sorry, I didn't write down the formula for Chern-Simons functional, but if we look at the generators of the Instanton Chern complex, right, this corresponds to the critical point of this Chern-Simons functional and mod out the symmetry. And so this actually corresponds to the set of flat connections over this SO2 principal bundle, of course, mod out the gauge transformation. And it is also known that, well, if we have a flat connection, what we can do is we look at the holonomy around associated to the connection. Because it's flat, this holonomy only depends on the homotopy class of the path. And so this corresponds to the group homomorphisms from the fundamental group of Y to SU2. And this symmetry becomes the conjugation of the SU2 group. So finally, our conclusion is that, well, the generators of this Instanton Chern complex that corresponds to SU2 representations, not with conjugations.
So you take components.
Excuse me?
You take components of because like you have families of connections.
Right. Let's see. I think this is a one-to-one correspondence, right? So as long as we have flat connections and then we quotient out with the gauge transformations, then that corresponds in one-to-one correspondence with SO2 representations.
My question is that for I don't know Stanford manifold with 4 single fibers, you have a more light space of connections, right? So so the generators of this finite dimension vector space correspond to the components.
Let me see. I don't think so. Yeah, maybe we can talk later, but
Okay.
yeah. So so essentially, yeah. First, well, we need to do some perturbations on that Chern-Simons functional, and finally, what we can achieve is that, well, after those perturbations, we only have a finite number of points as the critical points and the generators of the Chern complex in the end. Yeah. So
I guess one thing you could say is that we only have the trivial SU2 representation.
Right.
Right.
Right. Yeah, so let's say if we have just like the S3 and there's like trivial fundamental group and there's only the trivial SO2 representation, and if we put things in the best form, then we can just say the Chen complex is one generator with no differential. So homology is one dimension. So right, and this is the first thing I want to stress, that the Instanton Floer homology that has close relation with the SO2 representations of the fundamental group. And the second thing is that, well, this Instanton Floer homology constructed where this solving this set of differential equations, we need to understand what's the critical point of Chen-Simons function, or we need to understand how to what's the negative flow lines. So it's almost impossible to compute the Instanton Floer homology via the definition or via the construction. Yeah. So we didn't expect that we can solve that set of partial differential equations and write down the chain complex explicitly. And so this makes the computation of Instanton Floer homology a big problem. But on the other hand, we have this good relation with the SU2 representation. Many applications derive from this side, and so this gives us, this motivates us to understand that if there's a possible way for us to do some computation in Instanton theory, and also that motivates our so how to compute. And so this motivates us to develop this surgery formula, which actually help us in doing some computations. And also some other motivations. For doing the surgery formula. Is that, well, the Instanton Floer homology is just one version of the Floer theory that has been known. So there are other versions. Of Floer theory. Like there's the monopole Floer homology. By Kronheimer and Moroka. And also there's the Higa Floer theory. Higa Floer homology by Ellsworth and Stubble. And also there's the embedded contact homology by Hutchings. So, right, so it's a big problem. It's a big question whether all these four versions of Floer theories are equivalent to each other. Actually, it has been shown by Thompson, Honda, sorry, calling Honda, and then others. So there's many groups of people who have shown that the monopole Floer homology, Higa Floer homology, and embedded contact homology, they are isomorphic to each other for giving close-oriented three manifolds. But however, this Instanton theory kind of like remained and isolated, and we don't know if Instanton theory is also isomorphic to the Reg 3. But there have been known to have a surgery formula. There are surgery formula. Known in this Higa Floer setup. Right. And the surgery formula and Higa Floer setup have been very useful in developing some applications in three-dimensional topology, and so this gives us a second motivation to develop a formula also in Instanton theory. So there are some distinct merit for the Higa-Floer theory and the Instanton-Floer theory. For Instanton, we have this SU2 representation things, but for Higa-Floer theory, they're more computable. So if we can kind of like combine the advantages from different theories, we would be able to develop some new applications. So that's kind of like the motivations why we're interested in this surgery formula. So yeah, let me actually tell you what the surgery formula are about. So here's the surgery formula. So right, and for the moment, let me be specific to the case where we have a S3 and a not K inside S3. So our surgery formula can deal with general setup, but for simplicity, let me only present things in the case of three sphere, not inside three spheres, and so it's a knot. And so on one hand, we have this. If we have this knot K inside S3, what we can do is we can do dense surgeries to get some other three manifold. And because we're in F3, we have the separate framing, and so all different possible dense surgeries are parameterized by a rational number. And so on this end, we have the Instanton Floer homology for knots, right? And on the right-hand side, we have the Instanton Floer homology for the surgery three manifold. And so the question is, well, can we possibly relate this to object? So can we understand some information about the Instanton Floer homology of the surgery three manifold out of that of the knot? So that's the idea for a surgery formula, right? So
is this for a large value bar or like?
That's a great question. So right, so there's a few steps to establish surgery formula. The first step is to deal with large and integral number of R, and the second is to deal with a general integral number, and then third is to deal with an arbitrary rational number. So we were able to deal with an arbitrary rational number, but I'm only going to talk about integral numbers for this talk. The surgery formula to understand the Instanton Floer homology of the surgery from some information on the Instanton Floer homology of this knot. So the reason that we want to go from the Instanton Floer homology of the knots to that of the three manifold is that actually we know more about the Instanton Floer homology of the knot. So we know a lot about this Instanton Floer homology of the knot here. So for example, well, so remember this is a finite dimensional vector space associated to the knot, and so the first thing is that, well, this Instanton Floer homology decompose along integers, well, which is called the Seifert grading. This is the Alexander grading. Right, and because it's a finite dimensional vector space, if we look at the decomposition, only finite many terms could be non-trivial. And it is known that, well, this top non-vanishing grading is related to the Seifert genius of the knot. So G of K, this is the Seifert genius of the knot. It's a maximum S, so that this Instanton Floer homology is non-trivial. And also there's some more information about the fiberness of the knot, right? So we know this genus of K, this gives us the top non-vanishing grading, and K is fibered if and only if the corresponding top grading is one-dimensional, right? So we have complex vector space, so C is one-dimensional stuff. And also, well, there is the there's a spectral sequence from the Hobanel homology, actually the reduced Hobanel homology to the Instanton Floer homology of K with so K bar is the mirror of K. So actually a more precise statement is that there's a spectral sequence whose second page is the reduced Hobanel homology, and finally the spectral sequence converges to the Instanton Floer homology of the mirror. So all of these are works of Kronheimer and Morotka. Right, so and yeah, so maybe I forgot to say one more. So maybe I should. So one last thing is that, well, if we look at these gradings, right, then there's an actual grading, which is a homological grading on the Instanton Floer homology, and we can take the homological grading of each Alexander, the Euler characteristic with respect to the homological grading for each Alexander grading, and then we can get a polynomial here. So if we take this polynomial in T, that's the various S, and then we take the Euler characteristic. And put this grading to be the powers of T, then we get a polynomial, and this is the Alexander polynomial. Okay, right, so all of these are due to Kronheimer and Morotka. Yes, so yeah, I didn't say too much about that thing. So there is a Z mod 2 grading, a homological grading that is compatible with this Alexander grading. Or we can see for each Alexander grading, for each graded part there is also a Z2 grading, and so that we can take all that characteristic with respect to that Z2 grading. So that gives us the Alexander polynomial of K. So right, so all of these are informations that we can get from the Instanton Floer homology of knots here. But we don't know too much about the Instanton Floer homology of the surgery manifold. So that's why we want some relation between these two objects. And on one hand, we have more information, we have more knowledge to study about, and on the other hand, we know less. So that's the surgery formula. Yes. Yes. Any other questions? All right. So now let's try to state the.
Sorry, I
yes.
have a question.
Yes.
Besides the Z2 grading and Alexander grading, is there like another grading?
That's a good question. Yeah. So currently there's no. Well, let's talk about the Higa Floer setup. There's the so the Z2 grading is actually a Z grading called the Maslov grading, and so we can add the two things and get the delta grading. But unfortunately, in Instanton setup, we only have a Z mod 2 grading here, homological grading here, so we don't have an actual delta grading in Instanton setup. Yeah. Other gradings. Currently, I don't know, but let's say if we have a knot inside a solid torus, there could be an actual grading coming from like the meridian disk of that the meridian disk of that solid torus. Right, so if we have more structures, then we could possibly have more gradings. Other questions? Okay, so now let me try to formulate the surgery formula, right? So how can we possibly get to the surgery three manifolds here? So construction, right? So the first thing is that, well, as a work by Ben and I is that, well, there are differentials which we can construct on, well, let me say we have this knot K inside that 3. And those differentials are maps Ij, which goes from the Instanton Floer homology of Ki to the Instanton Floer homology Kj. Well, this I and j, they are the Alexander grading of the Instanton Floer homology. And right. And so, of course, well, we call them differential because, well, if like 2k equals I plus j, then the composition will be 0. So let's see, from k to j, I to j, I to k. This will be 0. And so maybe it is good to have one example. So let me take K to be the trefoil. And let me see, this should be the right-handed trefoil. Right, so the Instanton Floer homology of the right-handed trefoil can be pinned down by looking at this this Alexander polynomial and also the Hobanel homology. And so the Instanton Floer homology of this knot K, I will use like 3 dots. 1 dot denotes one generator of the Instanton Floer homology, and they're in grading 1, 0, and -1. So they're the grading, and this is the generators. Right, and so we have this differentials for all different I and j, and so we probably have I larger than j or I smaller than j, and so I will use 2 different colors to denote those 2 arrows. And in this case, we just have 2 such differentials. Of course, in general, we might have differential go from gradient 1 to gradient -1, and maybe from gradient -1 to 1. But for the special case, we don't have such. So, and we need to define.
Sorry, what's the formula at the bottom there?
This one?
Yeah, with the,
Oh yeah. So essentially, this means, well, the composition d squared equals 0. Yeah, but they're for different gradings. So maybe this curly K.
where does J come into that formula? Or sorry, I.
I here. Oh yeah. Yeah. Sorry. So that's kind of like shaded. Yeah. So the composition being 0, that means this is the differential. Yes. And so right. And then what we do is that we need to take and also yes. So we need to take what is called a band complex.
And why do you need this 2k plus I plus j?
Oh yeah, so right. So yeah, so essentially we have a set of differentials like yeah, I didn't explain that too much, but yeah, so essentially right, so we can treat like if we have like I minus j equals 1, then we have like a set of differentials just like going up by ones and going down by ones. And so maybe in general, we could possibly have something like just draw a very rough picture, something like that. And so there's no differentials composition being 0. And so this kind of like a way we can filter those differentials out. And when we might also have like differentials which going cannot be that, but maybe when we jump 1 gradings and have like things up. Yeah. So there are all different differentials. there. Right. Okay, so
Are there analogous differentials in the LHS-Lavos circuit?
that's true. Yes. Yeah. So we believe that for them, well, this is just like, yeah. So for Floer homology, that is a doubly filtered Chern complex, and so if we look at the Chern complex for the three manifold, that is just one base point, and so actually, the other base point gives us a filtration, and if we look at the top grading, the top filtered part, and that gives us the differential for the not Floer homology. And so if we look at the the other filtered part, that will give us the other differentials here in the following. Yeah. So there should be some analog in the Oswald-Szabos case as well. Okay. So. And the Stanford complexes are defined. So this is a band complex, HKHI, 3K. Right. So the vector space are the same, right? So we just always look at the not Floer homology, but we look at some different differentials. So with this S in Z, right? So maybe let me also draw that three different pictures here. So for HS, we specify this grading, and above this grading, we just only look at arrows which goes up, and below this grading, we only look at arrows which goes down. So if S equals -1, so starting from -1 grading, we just look at arrows going up, and so we have this thing. And if we look at S equals 0, then what we get is that above S equals 0, we have arrows going up, and below we have arrows going down. So we have this full thing. And if we have S equals 1, then we only have arrows which going downward. So
is this complex also, should we think of it as a filtering version of the instant complex for S3, or is it like the generators are, or is it the complement of the trefoil representation of the complement? Like what is
yes.
Yeah.
So right. So if S is large or small, then that gives us the instant Floer homology of S3. So let me write it down. So recall that if this S is larger than the genuines of K, then the graded part will just be 0. So we can define this B plus of K, this B plus complex to be AS for S smaller than -G, and we define B minus to be AS for S larger than the genuines of K. Well, there's only arrows up, and there's only arrows down. So that's why I put plus and minus here. And well, we can show that if we only look at those arrows which are up or down, then that will give us the Instanton Floer homology of the n-band 3 manifold. So
that works in general?
Yes, that works in general and works for any pair of K of Y and K where this K represent a zero homology class in the first rational homology of Okay, so other questions? Yes.
I'm sorry, but I can only understand things like by analogy to Hagar Floer for this stuff. So I want to make sure I have the right picture in my head. Like, should I be thinking of your like up and down arrows as kind of like the z plus d with like all these arrows in a different way, but we don't have two directions because you don't have a full second z grading?
Yeah, so let's see. Well, in Hagar Floer setup, maybe I can draw that picture for triple as well. So I guess, well, we have like I and j for their setup. And so so there should be like arrows go to the left and arrows go downward, and so that corresponds to UV filtration. So and that's like kind of like a yes. Okay, so in Hagar Floer setup, there are like so the band complexes are those hook areas, right? So yeah, so for example, this will be A0, and there will be A1, and also A-1. So right, so what you can make this analog to Hagar Floer setup is like we kind of like move those arrows which goes to the left, and we move it up. Right, so because in Instanton setup we only have this linear grading, so we don't have something that goes to the left. Yes.
Thank you.
Yeah. Okay. All right. So, and finally, we need to derive something, or derive a complex out of this AS and BS to finally get to the Floer homology of the surface ring manifold. So, there are two maps which way right. So let me say this. So let me right. So for S inside Z, so B S plus minus are identical copies of B plus and minus, right? And so we have maps pi plus minus. S goes from AS to BS plus minus. So I'm going to explain that by an example. So for example, this is the A0, and we also have B, let's say B plus and B minus. So B plus always goes up, and B minus always goes down. So suppose we want to define these two maps that goes from A0 to B plus and B minus. The thing is that we first do a projection, and then we do an inclusion. So right, so the way we choose this projection first will give us this different construction. All right, so now we have these maps, and there's one more thing we need, which is a translation, which we call tau n. This goes from B minus S to B minus S plus n. This is by identity. Right, so we know H1 is just a copy of B minus, so we just take this translation to go between different indices. And so finally, we're able to state the theorem about the surgery formula. Right, so let's say given K inside at 3. So what we know is that there is a quasi-isomorphism sigma from B plus to B minus. Right, so recall if we take the homology, they're both the homology of the n-density manifold. And so such that, well, if for any n, which is non-zero, I'm only going to state the integral version of this formula, but also that works for any rational number. There's a similar formula. So we can define a map Dn, which is, well, we have this pi plus, sorry, let me write it this way. So sum of s and z, we have pi minus s plus, there should be something is pi plus of s, and then I think we should first go to minus and then go deal with this translation. So let's see, yes. So we have a summation of two maps. One goes from is AS to B minus, and the other goes from AS to B plus, and then we use this closed isomorphism to go to minus, and then we shift this by n here. So this is the same n. And then the frame Instanton Floer homology of n surgery of K. This is isomorphic to the homology of the cone here. And there's some issue regarding the zero surgery, as because, well, yeah, so there are some problems about like choices of coefficients. So currently we could only deal with any non-zero surgeries. And there is a formula for any rational number which is non-zero, but the formulation would be more complicated. So I would just state the integral version here. Right. So maybe an example for n equals 1 is that, well, if we have a 0, a 1, a 2, a minus 1, a minus 2. And what we can have is that, oh, there's the b minus 0, b minus 1, b minus 2. Okay, so there are two maps. One is pi plus, and the other one involving pi minus. Yes. So if we look at those pi minus, that will just be and if we look at those pi plus, this term involving pi plus, the first is that we still go from a minus but to, a 0, say, to b plus 0, and then we switch to b minus 0, but there's a shift depending on n. So in the case of n equals 1, we just shift things to the right once. So I'll simply write it as pi plus. And so this is the big complex. Well, so this complex seems to be an infinite direct sum, but actually we can make a truncation to make it a finite chain complex. All right, any questions?
Sn and whatever these chain complexes, these two chain complexes, AS, CBS.
Yes, that's true. So essentially what we do is like we prove an exact triangle for, right, yeah. So, but the thing is actually even more complicated. Yeah. So if I have time, I can explain a little bit about like what's really the case for this isomorphism here. But yeah, let me first say something about the applications. So, yes. So the first application, of course, well, this is a formula, and we can, although it's formulated in this kind of like complicated way, actually in many cases, we are able to understand all these maps, like this pi plus, pi minus, and this, actually this quasi-isomorphism, and also this challenge. So in many examples, we can understand everything and then try to compute the incident Floer homology of dense surgeries. And so I just give some examples of such. Well, like let's say if we have a all genus one alternating knot. Or we have some families of appraisal type. Alternating knot. And well, we can also deal with all twisted white hat doubles. And this is like we take the set liking operator with this pattern. Well, here's the twist. Right. So we take this as a pattern and then take the set liking operation. And also, well, this connect this Borromean knot. In two copies of connect sum of two copies of S1 times S2. So this is a knot. Well, let me see if I could draw it. We have this knot B here. And so what we do is that, well, we have this three-component Borromean link, and we take zero surgeries on two components, and the third component remains a knot inside the connected sum of two copies of S1 times S2. So, so if we do dense surgeries, then this gives rise to circle bundles over surfaces. I think, and so if we take G copies of Borromean knot and take N surgery, I think that's give rise to circle bundle isola over N over a close-oriented surface of genus G. So a second application, yeah, first there's many more knots we can deal with. I just have a sublist of possible examples.
And this is like so. Were there other methods to compute the Instanton homology for these manifolds, or?
I think this is, yeah, for many of these, I think that's the first possible, yeah, it's the first appearance of those complications. So before we don't know what's the incident Floer homology. And I think especially for this example, because, well, previously there are some other techniques which mostly deal with knots in the rational homology spheres, and this should be the first example where we can deal with knots in some other three manifolds. Okay, and great. So the other part is that, well, we can use this surgery formula to understand the SU2 representations of the pi 1 of dense surgeries. Right. So for example, there's a general question to ask is that, well, for K inside that 3 knot and N knot, and does the pi 1 of S3 minus the neighborhood of K, so not complement, sorry, what am I saying? So does the fundamental group of R surgery of K admit an irreducible SU2 representation. Right, so irreducible means, well, if we look at the stabilizers of the image of this representation, that should be the center of SU2, which is plus or minus 1. So actually, it's a conjecture that if R is smaller than 5, then the answer is yes. So so why we focus on R smaller than 5? The reason is that if we look at the 5 surgery on a right-handed trefoil, this is the length space. So its fundamental group is sigma 5, which is an abelian group. So so this image in any SU2 representation is also abelian, which has larger stabilizers. So and another remark is that, well, the case of 1, right? This is the final case for the property P conjecture. Actually, I should say that implies a property P conjecture. Property P conjecture says, well, if we have a non-trivial knot in S3 and we do any dense surgery, we cannot generate a simply connected 3 manifold. And so for denominators larger than 1, of course, well, this cannot be simply connected. And for a denominator larger than 1, there's the cyclic surgery theorem. So the last case is the case of 1 surgery. And so it is a theorem by Kronheimer and Morka. That this is yes for all slopes at most 2. And so their proof uses, of course, Instanton Floer homology by showing some non-vanishing result that for smaller slopes, we can just look at, well, the dense surgery is like gluing 2-3 manifold with toroidal boundary, and we can look at the representation variety of SU2 representation variety of the towers, and then kind of like studying how this 2 representation varieties from the 2-3 manifold intersect with each other. So if the surgery slope is small, then we can derive the existence of irreducible SU2 representation directly. But if the surgery slope is larger, then there's not too many good results. And actually, they ask explicitly about, what about 3 and 4? And so these 2 other numbers, larger integer numbers, have finally been solved. The case of R equals 4, this has been solved slightly earlier, and then for the case of 3, this has been joint work by myself and 3 other collaborators. And we also deal with many other slopes. In this interval between 2 to 7. So, right, so the original conjecture is still open. We don't know if every slope with less than 5 satisfy this thing, but for many of them, here indeed. So if they do dense surgery, then the fundamental group admits some irreducible SU2 representations. Any questions?
What's known with R equals 5? I mean, you have the trefoil, but
Yes.
is that the only?
That's a great point. Yeah, I think seems like the only counterexample currently I know. I suspect that might be the only known counterexample. Yeah, as well.
Would you then? Would you conjecture then that is the only? If it's, if it's not the trefoil, then not the trivial, then
yeah, we might extend this slope, this bound a little bit further. Yes, yeah, I believe so, but I mean, I'm not sure. Yeah, I'm not sure if triple is the only counterexample for 5. Yeah. So, yeah, well, I mean, some counterexamples could only be some, let's see, Genius 2 fiber nodes, which, yeah, I mean, yeah, I'm not going to say more, but yeah, that's a good point. That's a good question. So, if triple is the only counterexample. So, other questions?
So, you know, it'd have to be null space. I guess, is that what you're saying?
Yes, yes. So, right. So the proof is like, well, if we have this particular surgery slope, and if the surgery ring manifold does not admit any irreducible SU2 representations, then all the reducible SU2 representations factor through H1 instead of pi1, which is simple for us to understand. And so actually we can write down all these reducible representations, and with some work we can show that they generate the Instanton Floer homology group. Actually, they're the generators of the chain complex, and there's no differential. So we can actually write down the precise dimension of the Instanton Floer homology group. And using the surgery formula, we can say something about the knot, right? So we're going the reverse direction. We already know the Instanton Floer homology of the surgery string manifold, can go back to say something about the topology of the knot, and that help us to pin down what that knot could be, and then we just rule out those kind of candidates exclusively. And so finally, yes. So for R equals 3 and 4, we don't, any non-trivial knots have irreducible superposition. Yes. Okay. Other questions? Or I think I should just stop here. And so anyone have